talk about objects on an incline today. So to do that first, I want to review a couple of our forces that we've talked about because we've started to make assumptions about our forces that we need to readjust a little bit. Okay, the normal force is the force of the surface pushing up on the object. So most of the time, what direction does that go? Straight up, right? But it doesn't necessarily mean that the normal force always points in the exact vertical direction, right? If my object is on an incline, so here's my object, does the normal force go like this? No, it goes, boom, right? It goes perpendicular to the surface, right? Here's my incline, here's my object. So my object is being pushed at that certain angle. Okay, so now our way of thinking shifts a little bit. Okay? So we need to remember normal force means perpendicular, not just straight up. Okay? What about the gravitational force? Where does that go? Still straight down. Yeah, still always straight down. So if I bring my if I bring my little drawing back, I've got a normal force that goes perpendicular to the surface, and I've got a gravitational force that is pulling straight down. Do those two offset each other anymore? No, they don't. They don't pull with equal strength in opposite directions. So that's a problem, right? We don't have things that are directly opposite of each other anymore. Okay? So if I'm pushing something up the incline, right, it would look like that. If I'm pushing something down the incline, it would look like that. Right? There's lots of things that we need to think about here. But the way we're going to be able to avoid as many angles as possible is we're going to rotate our axes to sit along the incline. So here's our coordinate system, right? Here's our incline. That means the positive x-axis is to the ground, right? The positive y-axis is there. Negative x and negative y. So all we're going to do is shift our axes. That allows us to have a normal force that's not at an angle anymore, right? Our normal force would still technically be going straight along the y-axis. If we had applied forces or frictional forces, right, they go along the surface. So this allows us to keep as few forces as possible using angles. Does that kind of make sense? So we're trying to eliminate us having to break down 3 different triangles just to keep gravity going straight down. Okay, are we on the same page there? So if I have gravity, let me just clear this out real quick. If I have normal force, friction, applied force, and gravity, and I kept my normal coordinate system, right, 3 of my forces would be at angles. That's no good, right? My normal force would be at an angle, my frictional force and my applied force would all be at angles. So that's not easy for us. The easiest thing we can do is curve or tilt our axes so that now our normal force is on the axes, our applied force and our frictional force are on the axes. The only one that's not is our gravitational force. Okay, does that kind of make sense? Okay, so we have to break down that gravitational force into its x and its y components, right? Because we don't deal with things at angles. So when we break that down, it's going to look like this. Okay, let me put that back up here. Oops. Horizontal component is going to be called the parallel component. Okay, and let me draw that gravity triangle out here a little bit more. Okay, here's our gravity force, and I'm going to draw the components here in yellow. Okay, the horizontal component of FG is called F parallel. That's not like F11 or something, right? Parallel. And why do you think it might be called F parallel? Yeah, perfect. It's parallel to the incline, right? It's pulling us in the positive horizontal direction. Right? Most of the time, which is our object going to slide? Is it going to slide up the incline or down the incline? Down. So that's why we're making that the positive direction, right? It keeps our numbers positive most of the time. Okay, so F parallel is pulling us downward in the positive x direction. Okay, can we see how that works? Okay, we could also like tack this on up here, you know, right, and say that's F parallel. We don't really need to do that, but we can. That's essentially what's happening, right? It's pulling us in that direction. Our vertical component now is called the normal force because it matches the normal force above the x-axis. Okay, so these two should be identical to each other. Okay, assuming there's no other vertical forces acting, the normal force here and the vertical component of our gravitational force should be congruent forces. Okay, or equal forces. So the way now we solve for the normal force is we find the vertical component of Fg. Right, and that would give us now the normal force. Okay, is the diagram making sense? Would it make a difference if we drew our incline this way? Okay, let's see. If we drew our incline here, right, now we still have Fg going here. We still have F parallel and normal. Okay, and normal is still opposite. Sorry, I'm backwards. We're going to look at this angle right here. So normal is still the adjacent force and parallel is still the opposite force. Okay, here's how we find this angle. The angle that our incline is to the ground, which is here, this angle matches our gravity triangle. Okay, so when we start saying we're sitting on a 30-degree incline, that means that in our gravity triangle here we have 30 degrees. Okay, so it's always the angle that's touching the incline. Does that kind of make sense? So the angle of the incline itself matches the angle within our gravity triangle. Good. Okay, so we've got a 10-kilogram box sliding on a frictionless surface. Here's what our diagram looks like. Fg is going to be mass times 9.8. Maybe we can do that without our calculators. Maybe. You just got to check, yeah. Okay, so that means that Fg, or the hypotenuse of that triangle, is 98 newtons. Okay, so what would this vertical side of my triangle be called? This one? Good. Fn, and then the horizontal side is parallel. Good. Doesn't matter which of those we solve for, okay? And realistically, for this problem, we want horizontal acceleration, so do we need the normal force? No. If we were dealing with friction, then we would, right? With friction, we have to have the normal force. But with this one, we don't really need to solve for it. It's never going to hurt you to have it, but for this one, we don't really have to have it. Okay, so F parallel is the opposite side, so we'll take 98 times sine of 30. Make sure your calculator's in degrees, not radians. I shouldn't have even said it. Okay, so now we've got our horizontal component at 49. Now we want to find horizontal acceleration, so we set up our net force equation. F net in the horizontal direction is F parallel minus anything? Do we have any leftward forces? No, right? F parallel is still a horizontal force. Once we break that down, that Fg, we don't use that in our problem anymore. Right? We use the purely horizontal and purely vertical forces. So F parallel is our only horizontal force. So we'd say 49 is equal to mass times acceleration. And we get an acceleration equal to 4.9 meters per second squared. That's right. So when it says it's already in newtons, a 466 Newton object, is that its mass or is that its weight? Weight, right? Mass and weight are two different things. Mass is always in kilograms. Fg, or its weight, is always in newtons. So this being in newtons already tells us that that's what Fg is equal to. Okay, so the hypotenuse of our gravity triangle is already 466. Okay, and our angle we know is 33.3. So I'm going to solve for F parallel here. Do I need the normal force in this case? In this case, I don't, right? I don't have friction again. So when we deal with friction, we have to have the normal force. When we don't deal with friction, we don't need it in this case. So F parallel, I'll take 466 times sine of 33.3. Is that what we got? 255.8? Okay, for these parallel and normal components, you can memorize that F parallel is always sine, F normal is always cosine, right? You can just look at the triangle too, but you can memorize that. That's one that won't change. Okay, our overall goal is to solve for what? What's the overall goal of this problem? How long will it take? So time is our overall goal, right? We know the distance here is 8.45 meters. So we want to solve time. We know our distance. We're going to have to use our kinematics equation, right? Have we made that connection? So what here are we going to be able to solve for to get to our kinematics equation? Acceleration. Good. So we're going to solve for acceleration. So again, our net force is just going to be F parallel minus 0, right? You can leave that minus 0 off since that's our only horizontal force. That's fine. You can put it there if that makes you feel better. But we don't know the mass, do we? Because we know the weight. Good. If Fg equals 466, we're going to take mass, which we're trying to solve for, times 9.8 equals 466. So we need to divide that by 9.8 to solve for our mass. Okay, does everyone understand why we did that? You can't plug in Fg for mass. It's not the same thing, right? Fg is weight. So for mass, I had 47.6 times A equals 255.8. Okay, that box is moving pretty quickly. Or it's accelerating pretty quickly. So now we use our kinematics equation to solve for time. What do you think our best bet for kinematics equations would be? Probably the second one. We know it starts from rest, so our initial velocity is 0. We know our distance final, our distance initial is always 0. And we know our acceleration. So I would agree, the second one. So x equals 0 plus 0 plus 1/2. Oops, that's not x. 8.45. Make sure you don't forget to square root your time. Okay, we should combine those first 5.38, divided by 2, and then you divide that over. Did you subtract it over? Okay. Since it's part of a single term, We need to divide that to get rid of it, or to get t by itself, and then we square root t. 1.77 seconds. Agreed? Okay, let's try some now with some friction. You can try it with the person next to you or in a little group if you want. That's fine.
What are we solving for?
I don't know. Acceleration, sorry. I did too much work on these PowerPoints, all these extra questions. Acceleration of the box. There we go. I'm just going to rewrite that so I have some room to do stuff. Okay, so you're solving for acceleration. That won't always be the case. For some reason, all my examples are solving for acceleration. Not always how it goes. We've got friction. We've got, we're going to need the kinematics equation to solve for how fast will it be moving. So you're going to solve for final velocity here, assuming that it starts at rest. Okay, let's try this one on your own.